So last time we got to the point that an elliptic curve is a plane cubic, non-singular with at least one point. And I showed you in Magma, Harris showed you in Sage how you can transform any such cubic. There is a method to go there. So there is a handout on the website. I'll show you. There is some paper that a friend of mine, Ryota Matsura, wrote a while ago. So here, I put it here. How to transform a general elliptic curve into Weierstrass normal form. You can read this. There's a short version of this in Silverman's, like this Silverman, and Kate. It takes rational points on elliptic curve. There is a brief mention of this there, but Ryota really explained this in a lot of detail with an explicit, a couple of examples on how to do it. So if you're interested, I think it's actually a very nice argument of how to do it, and you can learn how to do it. But for now, from now on, we consider all the elliptic curves are given in Weierstrass form. The long Weierstrass form is a form like this. If you don't know what the numbering of the coefficients y is kept 5, if you don't know that, then ask me at some coffee break, and then I can explain the weird reason for that. And it's not actually, the reason is nice, it looks at first a little weird. And the short Weierstrass forms, you can bring these to even shorter, and you can bring them all to have just integer coefficients, okay? And in this particular case, so we can bring it to A, B integers, and as I said at the very beginning, you can bring it so that 4a cubed plus 27b squared is not 0, and that just takes care of the singularities. As long as that doesn't happen, this polynomial does not have repeated roots, and then there are no singularities, and you have an elliptic curve. Okay? That quantity, usually there's a constant of -16 times that is called the discriminant of the elliptic curve. So there is a point on these curves. It's not obvious from this form. As I said at the end of last class, all my curves are projective in my mind. The good thing about these models is that it only leaves one point outside of the affine plane. There's one point fixed rational point O, which is in projective coordinates 0, 1, 0. If you don't know a lot about projective space, there is one of the appendix in the book is about projective space. So this point is called the point at infinity. And as I said, is the unique point at infinity. You can prove that if you haven't done it. Okay? So the question is, like in the case of convex, can we find all the points using some sort of stereographic projection? Can I trace a line from O and try to capture all the other points? And that's the answer is no. So can we find all points using stereographic projection? Well, no. Why? Because we have cubic equations, not quadratic equations. Okay? Okay. So why is that so? Because if I have an elliptic curve, it's something like that, and if I have a point O, and I try to trace a line that goes through O, yes, I'm going to have two other points, but those are not necessarily rational anymore. If this is rational coefficients, the line has rational coefficients, the equation of the curve has rational coefficients, I could still just put that all the information in, and what I'm going to get out is that the x-coordinates of these points satisfy a quadratic equation, but a quadratic equation doesn't have to have all rational solutions. It could be a pair of conjugates, of real conjugates, for instance, or complex conjugates. Okay? So they don't have to be rational. However, if I have that one rational and this one is rational, now this one is going to be rational. So I can use that to create points. So there is a method. This method, I've read somewhere that it was Newton's favorite method in mathematics. I don't know. I'm guessing that someone who really likes elliptic curves said that. But okay. So however, if we are given 2 points that are rational on an elliptic curve E, here's my curve E, and I have P, and I have Q, and those are rational, then the third point of intersection will also be rational. Okay, because now I have a cubic equation intersect with a line. I get so a cubic in 2 variables intersect with a line. Now I get a cubic polynomial with 2 rational roots. Then the third root should be rational also. Okay, and it is. So we use this to define an addition on elliptic curves. So we use this to define addition of points on E, and I'm already regretting I said this here, but so even if I have an elliptic curve in any form, any cubic form, I can define addition as follows. So I have an elliptic curve. You know if it is an elliptic, if you do any line, there should be there is a cubic plane, a plane cubic curve if any line intersects at most at 3 points. Okay, so let's see if I did it right. So first of all, you need to have an O. Okay, so here is my O. This is my 0 for my addition, and now take 2 points P and Q, and I want to define P plus Q. So the way we define it is that, well, the easiest, what would look the easiest is I do this. This third point here is going to be rational, and call that P plus Q, but that has some technical problems with the sensitivity. So what you really want to do is, once you found that point, now reflect with respect to O, trace another line through O, and now this guy is also rational, and that is the one I'm going to call P plus Q. Okay? And this actually is going to be minus P plus Q, minus quantity P plus Q. But so let's see, in those models, in particular in the short Weierstrass equation, what does that look like? Well, if you have an elliptic curve in short Weierstrass equation, then they look typically like that, or there is a little bubble that is burst out of this. And where is O? are infinity, but I have infinitely many points of infinity. Where at infinity? Up. So sure, we can put it somewhere here. Here's O. But what is the property of this O? This property of this O, 0, 1, 0, is that every vertical line in the affine plane ends up meeting there. Of course, in the affine plane, they never touch. They're parallel. They're parallel and vertical. They end up in this line, at this point. And this is something you can also prove in projective coordinates, that every vertical line ends up here. So how are we going to define P plus Q? I have P, I have Q, and what I'm going to do is trace the line from P to Q. Here's my point R, and now I'm going to reflect it with respect to O, meaning that I want a line that goes through R and O. What line would that be? X equals the x coordinate of R. So I want a vertical line because that will go through O, and see where that takes me. So if I do the vertical line through R, that will actually go to O, and that will give me P plus Q here. Okay? So that's how you define addition on the elliptic curve. And I'm not going to do explicitly, but it's really nice to do this, actually explicitly do addition with equations. So try doing exercise 2.41 in the book. That's an exercise to actually do addition on your own. I'm just going to give you an actual example. So what points are on that elliptic curve? Can you tell me points?
-1, 0.
-1, 0. Somebody said another one. 0, 1. 0, -1.
2, 3.
2, 3. Another one.
-3.
All right, so so the curve goes like that. So let's do addition of P with itself. Where's 2P? How do I start to find 2P? Tangent. I need a line that goes through P and P. That, if you've done enough calculus TAing or if you've done enough calculus, that's a tangent line. Okay. So P and P, a line that touches at P twice has to be tangent to a curve, and it goes through that point. If that was a straight line and this was a perfect graph. Okay. So it goes through this point. So that is my R. In here, I have to reflect it, and here's 2P. Now I have to do 2P plus P. So I add 2P and P, and it goes through this point and reflect it. Since that coordinate y is 0, it goes to itself. So here is 3P. How about 3P and P? I go through 3P and P. I go through to P to do that. So 4P should be here. And now 4P and P, the line that goes through 4P and P goes through the curve at another time at P again. So that's P is my R in this case. And here would be 5P. And now I do 5P and P. The third point of intersection is O. Okay? So I go like this, I hit O, and now I have to go through O and O and see where I land. Where do I land? What's the line that goes through O and O, and where does it go after that? What's the line that is tangent to the elliptic curve at O? Knows? You know? triple tangency. So it's actually, so that's what it's called an inflection point, Weierstrass point there. That point is very special for the curve because it's a triple tangency, and the line at infinity, that line is actually triple tangent to the elliptic curve. That's actually something very peculiar that helps you go, that it's sort of like the key to go from any long cubic plane to one of the Weierstrass equations, because that's a peculiarity of O here. So if you are able to change coordinates in a plane cubic so that you find a rational point, and with your change of variables you make a triple tangency there, you are going to recover a Weierstrass equation for your curve. So that's a trick to do it, but that's easier said than done. Okay, so that is addition. If you've never done addition on elliptic curves, then you can use a package just to see more what happens. So I'm doing the elliptic curve y squared equals x cubed minus 2, and that elliptic curve has a point which is that what is it? 27 minus 2 is 25. So a cube minus 2 is a square, so the point 3, 5 should be there. So I say that like this: E has a point 3, 5. It's like if you're really excited that E has a 3, 5 as a point, and is it there? Yes. It doesn't complain that it's there. So now I can do addition on my elliptic curve 2p and 3p, and see what happens. So this is the coordinates of twice p and 3p, and I can do 1,000 times p. The output was too long, so this means it continues. The numerator continues. Okay, so that's, I don't know if you see the denominator start. Let me know. I don't know if it's numerator or denominator. You see the coordinates at that point. So they're not all so easy. What happened here is that I started doing that, and I came back to O. So this was 6p. Okay, so so p here has order 6, but on y squared equals x cubed minus 2, the point 3, 5 is of infinite order. How do we prove that? Well, that's a little tricky, but we'll get to that. Okay. So, what kind of points can I get? What kind of sense of points can I get on an elliptic curve? That's where the Mordell-Weil group comes in, where the Mordell-Weil theorem comes in. So the Mordell-Weil theorem, over Q is actually just the Mordell theorem. They proved it over other fields and proved it more generally for a billion varieties. So what it says is that, we mentioned this yesterday, that the set of rational points on an elliptic curve is actually a finitely generated abelian group. So what that means is that there is a finite set of generators. There's always a finite set of generators that you can try to find, and with those you can generate all the points by doing addition, by doing tangents and strings like that. You can find all the points. Okay, but the question is, how do you find all these generators? And algebra will tell you that a finitely generated abelian group is of this form. There's a torsion part, and then there is an infinite part. So this is a finite subgroup of points of finite order. Okay, so there's only, for an elliptic curve, there's only finitely many points of finite order. For y squared equals x cubed minus 2, there are none. Only 0, which has order 1, is of finite order. Okay? And this is the subgroup generated by points of infinite order by exactly Re, and this quantity is called the rank of the elliptic curve over Q. Okay? This is well defined. This is not so well defined. I can't tell you these are of infinite order. I can always, if I have a torsion point, I can throw one and I can find another set of points of infinite order of the same dimension. So, but this is just to indicate how many points, how many Z linearly independent points of infinite order are there. That's R, that's the rank. Okay? Okay, so what kind of examples of elliptic curves can we find? As I said, we really like elliptic curves because of the richness of the answer. Okay? We can have elliptic curves such as this one, where there are no rational points other than the point at infinity. There are elliptic curves that only have finitely many points. So this means that it's just an abelian group of order 6. So if you go back to it, how many points did we find? 1, 2, 3, 4, 5, and 6. This is all. There are no other points on this elliptic curve. There is elliptic curves that have rank but no torsion. So it turns out that this elliptic curve, this is a point of infinite order, and the multiples of itself generate all the points, the positive and negative points. Negative, you can also find the negative multiples, and all those generate. Okay, so these are all NP within an integer. That's all the points, and there are no torsion. Or you can find elliptic curves that have torsion and rank. This elliptic curve has a point of order 4. And also 3 linearly independent points of infinite order. Okay. So again, now the questions are. The question is, what are the possibilities for the pieces of the? This is sometimes also called the because of Mordell-Weil. This is the Mordell-Weil group. What are the possibilities for the Mordell-Weil group? Well, I know there are 2 pieces. So what are the possibilities for the pieces? What are the possibilities here? And what are the possibilities here? So now we know what are the possibilities here. That is, that was a conjectured twice and proved once. Let's see. And then the possibilities for the rank, as I mentioned yesterday, there's been sort of like a needle that over time people thought, well, the ranks are bounded, and then people thought the ranks are unbounded, and then now the needle is over to ranks are bounded, and I am a little bit more on the camp of the ranks are still unbounded. So there is, even in this room, well, John Boyd left the room again. So there's conflicting data on that note. Okay, so let's concentrate on something we know is the torsion subgroup for now. So what can we say about the torsion subgroup? So again, the torsion subgroup, that's something we can define very precisely. The torsion subgroup are those points on E that have finite order. Okay. So for instance, elliptic curves y squared equals x cubed minus n squared x. These factors is x times x minus n, x plus n. Those have points 0, 0, and n, 0, and minus n, 0. Those are torsion points of order, well, except, oh, these are points of order 2. And if you call these P, Q, and T, it turns out that P plus Q equals T. So what happens is that the 2 torsion, but in fact for these curves, it's all the torsion is Z mod 2 cross Z mod 2. So it's not Z mod 4 because even though there are these 4 points, none of them have order 4. They all have order 2. Okay, and that's actually how you build the 2 torsion. The coordinate, the x coordinates of the 2 torsion are always the roots, if any, of the polynomial in x in a short Weierstrass equation. That you can prove. It's one of the exercises in chapter 2. Okay. So let me show you an elliptic curve with a point of order 7. I have here one such thing. So if I do minus 1, minus 4, minus 4, 0, 0. So what elliptic curve is that? That's minus 1. And then the A2 goes here, so it's minus 4. And then the next minus 4 is the coefficient in y. And then 0 and 0, so it's that elliptic curve, has a point of order, has a 0, 0 as a point. So we're very excited that 0, 0 is there. And then calculate those multiples and see what happens. 4, 8, 1, 2, 2, 1. That's those are pre-projected coordinates. We can try again 1000p. See what happens here. It doesn't blow up to the sky in terms of the number of digits. It's 0, 4 again. Why? Well, let's see what happened. Sometimes it doesn't, it doesn't. So here are the multiples of p. This is 2p, 3p, 4p, 5p, 6p, 7p. 0, 1, 0 is the point at infinity. So 7p is out. Okay? So we have that. So p is a point of order 7. Okay? I can just verify that easily. I can ask magma, to be so kind, what's the torsion subgroup of this curve? And I just sent information to Australia, and Australia responded, it's 7. Yes.
Is it coincidence all coordinates are integers?
This is a very good question we'll get to. It is not a coincidence. It turns out, we'll spoil the surprise on the next page, that so there's a theorem. We're gonna say now, okay, how do I find all the torsion points? There's a theorem to do that, and that theorem will tell us that torsion points on elliptic curves and shows by the stress equation always have integer coordinates. So that's one trick to find them, and there's a second trick that really helps. Okay, so what are the possible torsion subgroups? You might ask first, what kind of torsion orders are there? Are there points for there 5, 6, 7, 8, 9? Where is the limit to that? And as I said, there was a conjecture of Levi that people seem to have forgotten, and then it was conjectured again by Ogg, with not just conjecture, but he actually had a lot to say about the classification of torsion points. And then we had to wait until Mazur from Harvard proved this in '77. He proved the following, that the torsion subgroup is one of the following. It can be cyclic. Is generated by one point of order n, with n 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. It skips 11. And then it can be bicyclic with m 1, 2, 3, or 4. Okay? And there is, for instance, there are proofs of why 11 should not be there. That is where the beautiful intersection of elliptic curves and modular forms starts to really come in and be handy. It's a really mutually beneficial relationship that these two objects have. Okay? Please remember to RSVP for the banquet. Okay, so by the way, so a lot of my own research lately is on this. This is what's already proved. What do you mean by this? Well, you can change the field here, and then the question is open. We know what happens of fields of degree 1, Q, degree 2, of degree 3, and that's it. So, but then you can ask different questions. What happens if I start with an elliptic curve over Q and go up to elliptic curve over another field, and then see how many points do I get if I